My name is Jennifer Van Saders. I'm a graduate student at The Ohio State University, and I'm here to report on a recent paper with Mark Pinsonneault, which is entitled The Sensitivity of the Depth of the Convection Zone to Stellar Abundances, an Absolute Stellar Abundance Scale from Asteroseismology. And I'm here to walk you through some of the basic points that we make in our paper. Now, the paper is motivated by the fact that in astroseismology we're sensitive to the acoustic depth to the base of the convection zone. And what we ask here is this astroseismic observable sensitive to composition? And if it is, can we use it as an atmosphere-independent absolute measure of stellar abundances? To do this, we construct a grid of stellar models, the results of which are shown here in Figure 4 from the paper. Both the x and the y-axis of this plot are astroseismic observables. On the x-axis, we have the mean density, which is related to the large frequency separation. And on the y-axis, we have the acoustic depth to the base of the convection zone, here normalized by the sound crossing time. You'll see that there are many curves, each of a different color, and each of these different curves represents models of a different composition. The uppermost red curve is for models of an Fe upon H of plus 0.6, and the lowermost curve, in purple, is for models with a metallicity of negative 1.2. The dark dashed curves denote lines of constant mass in solar masses. For models that are more metal-rich, we see that they have systematically larger values of the acoustic depth to the base of the convection zone, which denotes systematically deeper convective envelopes. Likewise, more metal-poor models have systematically shallower convective envelopes. To first order, we expect that the location of the base of the convection zone is set by the effective temperature, but to second order, composition also plays a part. Although the mass fraction of metals is small, metals have a disproportionate effect on the opacity, and the opacity in turn helps to set the location of the convective boundary. Therefore, more metal-rich models have higher opacities, become convectively unstable deeper in the interior, and have deeper convective envelopes. Now that we've shown that the base of the convection zone is sensitive to composition, we ask whether that sensitivity is large in comparison to theoretical and observational uncertainties. And the way we go about this is we assume some reasonable observational uncertainties for quantities such as the effective temperature, the helium abundance, the age, etc., as well as the astroseismic observables. And for theoretical uncertainties, we systematically vary the input physics in our models and ask how much it changes the observed location of the base of the convection zone. When we fold all of these uncertainties together, we find that we're actually sensitive to composition at the few tenths of a dex level, that if you go and you measure an acoustic depth to the base of the convection zone, you can measure composition to within a few tenths of a dex. This particular plot shows the results for a 5 gig-year-old solar composition object. And here we can measure the composition to within 0.15 to 0.3 dex. And this is competitive even with spectroscopic determinations of the composition. What we have here is an entirely new atmosphere-independent absolute measure of stellar abundances, which immediately lends itself to a host of interesting applications. If you'd like to read more about exactly what we've done and the details of our results and our methods and the applications that we propose, please take a look at our paper, which is posted on the archive today.